What is sprite stacking? Sprite stacking is creating a 3D effect by stacking images on top of each other to suggest height and depth. Today I'll be showing you how to recreate this effect and how it can be used in an RPG type game. I started with a pretty empty project. I have a player object which has some movement code in it and an empty tree object. As this is about sprite stacking, I won't be covering movement code, but I will be showing how to modify it to work with sprite stacking later. So next I will make 3 sprites. I will call them sprite tree, sprite grass, and sprite player. For the grass object, I'm just going to make it 128 by 128, and I'm going to make it green. Cool. And then I'm going to go to the room and tell the background to be the grass sprites with a horizontal and vertical tile. Next, we're going to go to the player sprites. Now we're going to keep it simple and just do a white square and copy that about 10 or so times. It doesn't really matter how many times. And then lastly, we're going to do the tree sprite. So I'm going to set this to 128 by 128. And I'm going to loosely draw a circle for green. And this will be the base of our tree. And we're imagining that we're making a tree by layering it with different branches as if you're making a Christmas tree. So we're just going to keep sort of making smaller and smaller circles until we get to a point. And then we're just sort of to pad it out. So we're going to copy each frame. Cool. So now we have our sprites done. So let's assign them to our objects. So I'm going to assign the object sprite, the player object to the player sprite, and then the tree to the tree. In the tree sprite, we're going to go into the create event and add some code. So first we want to tell the object that we want it to not draw itself, because we're going to get another object later to draw it in 3D. Next, we're going to get how many sprites the object has, aka how many layers it has to draw. And we're going to say how many pixels we want each layer to be apart from each other, layer heights. We want to do the same in player object. So if we just copy and paste that code, we can go into a create event and paste it. And I'm going to change the layer height to 5. Then we're going to create a new object called obj draw. And in the draw event for this object, we're going to add the code that allows it to draw each object. We want to first define the starting layer, which is n, and the final layer, which we're going to say is 200, which is m. We're going to tell the game to repeat everything m number of times. And each time we go up in n by 1. So it checks every layer. Then we're going to go inside the tree object and check when it needs to draw a layer. So if the remainder of n divided by the layer height is 0, and n is less than the layer height times the maximum layers, then we're going to draw the sprite. So we're going to draw sprite, and we're going to put in sprite index, floor, which we're going to say tell the game. We're going to tell the game what layer to draw. We're going to put just the regular x and y, but we're going to make the difference by -n. And then we're going to keep everything else the same. We go into our room and drag in a tree object. We need to drag in a tree object, a player object, and the drawer object. So now if we run the game, we should see that the tree now looks 3D. So we see that the tree is 3D and the player object doesn't draw itself because we told it not to. But this only works with the tree object first. So let's make it universal. So we're going to create a new object and we're going to call it parent sprite stacking. And we're going to make its children any object that we want to have sprite stacking in it. So in this case, the tree and the player. Then if we go into the draw event for the object draw, and then we can say that with all sprites that require sprite stacking to run the code to draw them. So if we now run the game, we're going to find that both the player and the tree object are now drawing themselves. See? So the next step, since we have a parent object, we can get all sprite stacked objects to inherit code from it. So if we create the create event and go back into a tree object, we can copy these two lines. Sorry, that should be the sprite index. If we then copy these two lines, we can delete them out of the two individual, and we can copy it into the parent. And then in the individual, we can tell the child to inherit the code. So we can say event inherit, and that's it. And it will inherit the create event from its parent. We do the same in the tree object. And we run it, we find that nothing has changed. This is mostly just to compact the code, so you don't have to change the code in a million places. It can just be changed in one location and it becomes universal across everything. As you can see in the game, you can't make out any detail of the tree or the player, so let's add some depth to that. So if we go into the draw event, we can add some code in front of before it draws itself. So we're going to say the color difference between each layer is going to be 10. Then we're going to say the color value for a given layer will be the maximum minus the max number of layers times the color difference. And that will give us our baseline, the bottom color. And then we have to change that depending on what layer we're actually on. And then we have to actually create the color we want each layer to be. So this will give us a gray that ranges from black to white, and it will tint our sprite it draws to the screen. And then where it used to say color white, we can change that to color. So now that we run the game, we'll see that you can make out detail of each layer. See? So that's all you have to do to get the sprite stacking effect. The game can then be programmed if it was an RPG, because the game thinks it's just a 2D game. You can just add in as many things as you want, and I'll show you how it can be an RPG quickly. And you just have to make sure that for every object you want to have sprite stacking, it has to have a layer height, and it has to be a parent of the sprite stacking parent, and let it inherit its code. So you can see that they can intersect and they sort of create a 3D effect. Next, if you want to get real fancy, we can add a camera. So if we create a new object, you call obj cam. In the step event, we can tell it where to go. We can say obj player.x, y equals player.y. So we're just telling the camera to go to the player. And let's drag that into the room quickly. And then we also need to tell the camera to move itself. So if we if we just find where the camera is, if we get the details about the camera, we can then change its values. And then we can set the camera's view position. We had to find the height and the width because we want the camera to be located, we want the player to be in the middle of the screen, not the top left. So we say what camera we want it to be, and then its location. We also need to make the camera. So we've made the object that's going to tell the camera what to do, but we also need to enable the camera. So if we go onto the side, do enable viewports, and then turn on viewport 0, we'll turn on the camera so the game knows what to read. So we find that now we can move around and the camera follows it. But because we have a 3D landscape, we aren't just limited to one camera angle. So now we can change the angle. So if we get the current angle the camera is at, and for this, we're going to make it a variable instead of just one that deletes itself after the frame. Next, I'm going to make it so the camera turns depending on how your mouse moves left and right. So first you have to find the position of the mouse. And then we need to find the movement the mouse makes. So for now, we're just going to do the change in the X direction it makes. At the end of every frame, we're going to set the mouse's position back to the center. We can then set the new camera angle the camera is going to be at based on the amount the mouse has moved in that single frame. And then dividing it by 5 is sort of the magnitude and the speed at which the camera rotates. So making that a smaller number will make the camera move faster around the player. So if we run the game now, we should find that we can move your mouse and it will move the camera around the player. So we'll see. And because we haven't tweaked some values yet, it looks really disorientating to the player because it just looks like the image that you're rotating the computer. And you might have a hard time closing it because the mouse is automatically to the center. So what you want to do is click Windows, and then you'll be able to move your mouse and hopefully be able to delete it. And we can quickly fix that. So if we create a new object, we'll call it game. And we can say, when you press the escape key, we can say game end, which means when you click the and put it into the room. This means when you click the escape key, the game will end and you won't have to fiddle around with your mouse, which is in the middle screen. In that game event, we also want to make the mouse invisible. So if we go into the create event, we can say Windows set cursor. We can say CR none. So this will just tell the game to make it itself invisible. So now you can move it around and you won't see the mouse except if it pokes out the top or the bottom. And then you can click escape to close the game easy. But now we need to fix it so instead of just like a rotating screen, it looks like the camera is actually moving around the player. If we go into the draw object, let's find some more temporary variables. So we need to know the direction the camera is currently pointing. Then we need to know how to find like the equivalent X and Y values. So we're going to use a trigonomic function just to save effort calculating. And if you know how vectors work, then what we're doing is finding the I and J vectors for a given angle. As you might notice, these aren't just what the camera angles. 90 is to say that we want it upright, because 0 would be right, they're pointing right. And then the negative is to say we want the inverse to whatever the camera is. So we want it to go the other way to counteract the effect of the camera. In the code down here, when we draw the sprites, all we have to do is get the camera direction for the X, times it by n, and then the same for the Y. So now when you run the game, you'll find that everything always points upwards, basically. I accidentally put in an underscore where there shouldn't have been. So now when we move it around, it looks like the camera's rotating around the player. But you might notice, no matter when I click W, it always goes in the same direction. And that can be really disorientating when you're playing. So what we can now do is tweak that using a similar technique of when we got the camera direction. So if we go into the player and go into the step event, we can find the new angle. There we go. Found camera direction. And then instead of just adding the X to the X and the Y to the Y, we're going to add the X component of the X plus the X component of the Y together to form the new X. So it's a little bit lengthy, but if you've done matrices, it's a similar process. So if I just point out the slight differences, the X in this row, both of these are X's, and then we've got the move X and the move Y, and then we're telling it to move horizontally, or the equivalent to horizontally, and the equivalent to vertically. And then we can do almost the same in second row. The only thing we're changing is changing the two X's to Y's to say get the Y component. So now when you play the game, you'll find that no matter which way the camera is pointing, the player will always move forwards, backwards, left, or right. So if I move forwards, you can see that the player, if I rotate the camera, the player also changes direction. So it always moves in relation to the camera. And that's how you get almost the whole way there. Then there are small things that I like to add to sort of make the game a little bit more smooth. So the first thing I like to do is adding vertical movement, because just rotating around can feel very stiff. So what I do is get the window height. I then change the window height depending on the location of the mouse. This value here is the height of the camera, which you can see off to the side. And then if I play this, you'll find that depending on where the mouse is, it warps the screen. So see, I go down, it stretches everything, I move up and it squishes them. Cool. But the next step is to counteract that. So if we could go into the draw event, the object draw, we can add a few lines. Cool, we're finding vertical angle. And then down here, we're just going to add that vertical angle to this huge multiplication we're doing. So if we now run the game, we're going to find that it looks like things are turning more opposed to just being squashed and stretched. See? A little bit more. It's not perfect because the way it's programmed, but it does the job of making the camera feel a lot less stiff, so you can sort of move around more freely. And that's it. Setting up sprite stacking and a camera automatically just works with your game because the game assumes you're just making sort of a top-down game. So you can create an RPG and make it have sprite stacking. In the game that I've used sprite stacking, I've added shadows by creating another draw layer that draws in a consistent direction and makes that black. I also add wind and trees by moving their location slightly using sine waves. And if I want to have like an animating player sprite, I switch it between different still frames and it looks like it's being animated when it draws. So hopefully this helped, and hopefully this allows you to sort of a grasp at sprite stacking and how you can implement it into your game easily. This is no means a total solution. There are plenty of things you can add, like the shadows and the wind that I described earlier, but it's a good start. So thank you for watching.